Hey everybody, this is a PowerPoint presentation of the conceptual points of Chapter 19, which is the Carboxylic Acid chapter. And like we've done before, we'll often have these little PowerPoints that have kind of highly conceptual concepts related to a topic, different functional groups, etc. I would recommend getting the PDF of this and ideally printing it out or putting it on your computer. Maybe taking notes for anything that that's not shown clearly on the PowerPoint. And yes, these kind of slides could potentially contain quiz material, so you should know this stuff. All right. And having it as a PDF allows you to kind of refer to it quickly during a quiz, rather than trying to watch the video again during a quiz. Okay. All right. So what are some carboxylic acids? A couple are here. Citric acid is a very simple one that's found in citrus fruits and limes and lemons and oranges. It's a tricarboxylic acid. There's 3 carboxylic acids and a hydroxy group. Acetyl salicylic acid is aspirin. This is a benzoic acid, so it's a benzene with a carboxylic acid, and there's an acetoxy group, which is the ester down here. Ibuprofen is another painkiller. It has an isobutyl group down here, and 2 carbons carboxylic acid. Naproxen is another carboxylic acid pharmaceutical. It actually is either naproxen, which is CO2H, the carboxylic acid, or the sodium salt of the carboxylic acid, which is the sodium carboxylate, is CO2 minus and Na plus. And this, why would this be maybe useful as a pharmaceutical as opposed to the carboxylic acid? A big reason is that the sodium salt usually makes it a more crystalline material, and for a pharmaceutical that's ideal. You'd rather have a nice crystalline material. The carboxylic acid originally is maybe waxy or maybe a different physical state. Okay, so what are some of the naming principles for carboxylic acids? If you have a simple hexane or like alkane, like hexane, then the carboxylic acid name would be hexanoic acid, right? Pentane, pentanoic acid. Okay. Now these are a couple of these have common names. Like this would be, I guess, using this nomenclature, it would be ethanoic acid, right? 2 carbons. It would be ethane, ethanoic acid. Nobody uses ethanoic acid. We call this acetic acid, though. Propanoic acid is a pretty common one, 3 carbons, propanoic acid. This could be butanoic acid, also called butyric acid. 1, 2, 3, 4, 5. Pentanoic acid could be this molecule. Okay, so ethanoic acid is generally considered or called acetic acid. It's a common name. Propanoic acid is the 3 carbon one. A common name for this is propionic acid too. Butanoic acid or butyric acid. So these are common names for these. I think the most common of these common names is acetic acid for this molecule. Pentanoic acid, 5 carbons. This is the common name of this one's weird. It's valeric acid. Generally, I'm not asking you to memorize common names, but these IUPAC names are pretty simple. Carboxylic acids take the highest priority in naming. So this looks like it's going to be a hexanoic acid derivative. Hexanoic acid, 1, 2, 3, 4, 5, 6. And it looks like we have a 3-chloro-4-methyl. 3-chloro-4-methyl hexanoic acid. This is a propanoic acid, and it looks like it's 2-bromo-propanoic acid. Here we have the stereochemistry. I'm not asking you to determine R's and S's in this course, but is S 2-bromo-propanoic acid. You could do the thumb method to confirm that. And yep, yeah, left hand S. Yeah. This molecule, well, the parent is benzoic acid, which is the the benzene and the carboxylic acid. This would be maybe 4-bromo 3-hydroxy, 4-bromo, 2-hydroxy, 4-bromo 2-hydroxy benzoic acid. It is also a salicylic acid derivative. I'm not going to go into that in depth, but remember aspirin. Aspirin's based on this part, the benzene, the OH, and the carboxylic acid, and that's called salicylic acid. So I think this could be called 4-bromo salicylic acid also. 4-bromo salicylic acid. But IUPAC is, a pretty nice systematic method. This would be 4-bromo 2-hydroxy benzoic acid by IUPAC. Common names. Okay, so these are commonly found simple carboxylic acids. We just saw acetic acid. What's one carbon less? Maybe it's formic acid, and this is the ant poison formic acid. This again we called benzene with the carboxylic acid, benzoic acid. This one we see from time to time is oxalic acid. Oxalic acid. The calcium salt of this, so if you take off the 2 protons and put a calcium 2+ in there, it's called calcium oxalate. This is the most common constituent of kidney stones. So they look like little bits of popcorn, but they are definitely not popcorn. These are very painful little rocks, little stones of calcium oxalate that go through your kidneys and cause extreme pain. So this is pretty much the cause of the pain in kidney stones. We saw this one already. It's a tricarboxylic acid with a hydroxy group. This is citric acid, found in citrus fruits. You have 2 carboxylic acids and 2 hydroxy groups. I think this is tartaric acid. Yeah, this is found in wine and other naturally occurring things like grapes. Tartaric acid. It does have stereochemistry, and there's actually 3 stereoisomers. There's I think the R. Let's see. I think it's RSSR, and then there's a meso form. You can see the different stereoisomeric forms. The top 2 are chiral, and the way you know that is you rotate the middle bond around, and then you see that it's wedge on the left. Dashes on the left, wedge on the right. When you rotate it, dash left, wedge right. And this one, it would be wedge on the left, dashes on the right if you rotate the bond. This one, if you rotate the bond around, you see a plane of symmetry. So this is the meso one. And so this is D tartaric acid, L tartaric acid, and then the meso one is actually not present naturally. So the naturally occurring forms of tartaric acid are the stereoisomeric forms, D and L. Okay. Dodecanoic acid, lauric acid. This is just a long chain carboxylic acid. How many carbons? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 is like dodecane would be a 12-carbon alkane. Dodecanoic acid is the 12-carbon carboxylic acid, counting coconut and palm oils. The structure of carboxylic acids is planar, sp2 hybridized, pretty straightforward, roughly 120 degrees per the 3 things. The H, the double bond O, and the other O are roughly 120 degrees. And the bond length of CH bond lengths are kind of short. This oxygen is kind of sp3, so roughly 109 degrees or so. So roughly follows like sp2 geometry for the bond angles. And the C double bond O is about 1.2 angstroms, I guess. And bond lengths do change, I guess, from different atoms to other elements. This seems a little longer. You might think it would be shorter because there's 2 bonds, but I think because the bond to oxygen is kind of a weak bond, it's a little longer in this case. Carboxylic acids often form these dimers, and they are hydrogen bond donors and acceptors. So two carboxylic acids can kind of form in this sort of complex. So a C double bond O of one talks to an OH on the other, and then a COH on one talks to the C double bond O on the other. And so they form these dimers, and that increases the boiling point. So the boiling point of carboxylic acids is maybe a little higher than like an alcohol or something, because you have this extra hydrogen bonding going on. In extremely dilute solutions, the dimer can be broken up. So, yeah, like dilution can break this apart if you dilute carboxylic acids kind of extremely. And very often carboxylic acids are freely soluble in like water, because they dissolve into water and they're hydrogen bonding with water, and that makes them nice and dissolved. So generally carboxylic acids are freely soluble. If you have a huge long R group, a greasy R group, they may not be soluble, and very often it would not be. But it's kind of small carboxylic acids, a couple carbons, they will readily dissolve in water. Okay, spectroscopy of carboxylic acids by molecular formula. If we have a carboxylic acid, of course, there's two oxygen. Whoa. What's it doing? I don't know why I did that. There's two oxygens and a degree of unsaturation. 1 second. Sorry, I'm getting my other mouse. Okay, two oxygens and a degree of unsaturation. So yeah, seeing a degree of unsaturation would give you a hint maybe that you have a carboxylic acid. If you do not have a degree of unsaturation, like you have UN equals 0, then that would suggest maybe, well, it pretty much cannot be a carboxylic acid, right? But a degree of unsaturation alone does not imply that you have an acid. But two oxygens is a hint. And by proton NMR, here's an example, and also the other hint is that there's a broad singlet around 12 ppm. So you have this in your little form. It's also on the syllabus, I believe, the little NMR chart, also on the exams. Also, in carbon NMR, you have a peak around 180 to 190. Generally, when I give you assignments, though, we're focusing on proton NMR. But carbon NMR, carboxylic acids, also esters are around the same range. There is another functional group that is way to the left of that, which is a ketone or aldehyde. Those are around 200 to 220. So you can distinguish a ketone or aldehyde from a carboxylic acid or ester or amide even, kind of by the carbon chemical shift. Okay? All right, so this is an example of a simple carboxylic acid, and we see the broad singlet, which is the OH on the carboxylic acid. It's around 11 ppm. That's a big hint that you have a carboxylic acid, is that 11 ppm OH. Okay, and then this is a very simple one where we just have a chain. There's no splitting or anything like that. But you have the CH3, this right side CH3. We're not showing integrations. Well, we give the numbers. So 3H, yeah, that's the CH3. And then you just have some CH2s. And we have 3 CH2s, right? 1, 2, 3 CH2s. Which one's the downfield one, which is to the leftmost CH2? Well, what do you think it is? Maybe it's the one next to the carboxylic acid. And remember our guidelines that we say things that are next to pi bonds, carboxylic acid is a pi bond. Things that are next to pi bonds are around 2 to 3. And there it is, right in the 2 to 3 range. What's the splitting of this guy? It should be a what? Should be a triplet, because there's 2 H's next door. So 2 plus 1 is a triplet. What's the splitting of this guy, the CH3? Well, it's also a triplet, because there's a CH2 next door. 2 plus 1 is 3. So these guys are triplets. The one that's a little more downfield is this one, I think. This one. Downfield. A little more than the other one. So there's two CH2s otherwise. The downfield one is a pentet. Why is it a pentet? P, pentet, because there's 4 neighboring protons plus 1 is a P, pentet. This one, if we zoom in on it, it would be a hextet, or sextet, because there's 2 protons on one side, 3 on the other. That's 5 plus 1 is a hextet or sextet. This is the carbon. It's very simple, and this shows the beauty of carbon NMR. Nice carboxylic acid at 180, and then we got the 4 carbons, other carbons, 1, 2, 3, 4, or probably 1, 2, 3, 4 in order, with the downfield one around 34 or so. Okay. This is a great problem, and we're on these quizzes. We're going to start having a couple NMR problems related to the lectures we're doing, and try this one. It's pretty easy. I mean, UN will probably be 1, and if you can't get UN equals 1, you need to let me know. I know I've said that 1,000 times, but you need to calculate UN. This should be the first step. Do the try to solve this carboxylic acid. It's not that hard. Okay. All right. Yeah, the D of 6H, maybe it's 2 carbons on a CH. That's a good hint, right? Okay. Carboxylic acids are readily acidic. They can also be a little basic. Here's an example of a carboxylic acid being an acid. So the carboxylic acid pKa is roughly 4 to 5. So it reacts with water in an equilibrium to make the carboxylate. That's a word you should know. Carboxylate is the carboxylic acid anion, and hydronium, right? Okay. And why are things like this kind of acidic? Because that is somewhat acidic compared to what we know. And the reasons it's acidic, in our general explanation for acidity in organic chemistry, is resonance stabilization of the conjugate base, right? So if the base, it could be water or something, takes off the proton, then you have this equilibrium not equilibrium, don't say equilibrium, resonance structures, right? So these are the carboxylate resonance structures. And this is pretty extensively stabilized by resonance. And that explains why we get a slightly low pKa, 4 to 5. Okay. Nearby electron withdrawing groups enhance acidity, make things more acidic. Let's look at a couple examples. The big one is that halogens. Well, actually, let's first look at the top two. This is acetic acid versus formic acid, and so electron withdrawing groups will enhance acidity and make the pKa lower. So electron withdrawing makes the pKa lower. Electron donating makes the pKa higher, and it destabilizes the conjugate base. What I'm trying to show is why formic acid and acetic acid have this appearance. Formic acid doesn't have anything on the carbon, right? It just has an H. And whereas a methyl, if I compare formic acid and acetic acid, the methyl is slightly electron donating compared to formic acid. And when you have that slightly electron donating group, it actually makes it a little less acidic, a slightly higher pKa, because it very slightly destabilizes the conjugate base, relatively speaking, between formic acid and acetic acid. So there's maybe that going on. The more profound effect is when you have halogens. So like a single chlorine. So this is chloroacetic acid, monochloroacetic acid. This is actually used as a plantar wart treatment. So if you get a plantar wart, it's a papillomavirus wart on your foot from going to the gym and getting like stepping on on basically somebody else's papillomavirus, you will get a wart on your foot. And this is a strong acid that eats the wart away. You can put this on your wart and it'll destroy it. It'll kill the viral growth on your foot. monochloroacetic acid. Anyway, so then we have like dichloro and trichloro. And as you can see, first of all, adding one chlorine really dropped the pKa. Almost, it's exponential. So this is like 100-fold more acidic than acetic acid. And that's why you wouldn't use acetic acid on your plantar wart, because it doesn't do as much damage to the tissue. Okay, so yeah, it's like 100-fold more acidic. And then as we add more chlorines, the pKa even drops more. So now it's 1.2. To add more chlorines, the pKa even drops more. Turn the chlorines into fluorines, and the pKa even drops more. So this is trifluoroacetic acid. This is a pretty strong acetic acid derivative. And also, if we add additional carbons to acetic acid, it increases the pKa. And that's what I was saying before about like these guys can slightly donate electron density into the carboxylate, and that's not a it's electron donating as opposed to electron withdrawing. And by being electron donating, it slightly destabilizes the carboxylate, and thus the pKa actually increases. Okay, and also the effect is distance dependent. So if I have a couple carbons and I have a chlorine on the alpha carbon, so the carbon next to the carboxylic acid, it's at 2.84. What if I move the chlorine one over to the left? Now the pKa increases a bit, and the chlorine even goes further, the pKa increases as well. So the effect is distance dependent. But we can still see that even in this bottom one, it's carboxylic acid, carbon, 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 and then chlorine. It still is a little bit lower than like this guy, the butanoic acid or butyric acid, because the effect travels through distance, through the sigma bonds, right? It's a sigma bond transmitted thing. What's that called? It's an I word. It's induction, right? Okay. And so why do we have this effect? We just mentioned it. Inductive stabilization of the conjugate base. So it's not really a resonance thing, it's an induction thing. And so TFA reacts with water. Water takes the proton, you make the conjugate base. And the carbon and the three fluorines, they stabilize the negative charge through the sigma bonding system. So you could draw little delta negatives on the fluorines, and that is delocalizing the negative charge through the molecule onto the fluorines, and that's a stabilizing interaction. And you get a lower pKa value. This becomes more stable. It's induction. Also happens for substituted benzoic acids. So this is 4-methyl benzoic acid, 4-methyl. Here's normal benzoic acid. Here's 4-chlorobenzoic acid. So what's the effect on pKa? Normal benzoic acid is 4.2. Add a methyl on the other side, and you get a 4.3, slightly less acidic. Add a chlorine on the other side, and you get it slightly more acidic. And the way I explain this is I consider the conjugate base, and I think of electron withdrawing group kind of pulling on the electrons through the molecule, through induction, and that's a stabilizing interaction. That's what we have in the chlorine one that causes the low pKa. And then if we have an electron donating group, it's the opposite. So electron donating group, and this is not a huge destabilization, right? But that's what's happening with the methyl. The methyl is pumping electrons in a bit. This negative charge is kind of putting its electrons in, and there's kind of a conflict, and that just slightly destabilizes the conjugate base, and you get a slightly higher pKa. Benzoic acid in the middle is the same. Benzoic acid is it's like the middle one, and it's the middle pKa. So it's like in between both of these extreme cases. Carboxylic acids can be bases as well, but only one of the oxygens is protonated. Why is that? So this is what we're doing here is we're looking at a carboxylic acid, and we're going to treat it with a proton, H+, and we're going to say which of the oxygens is the proton going to go to? Is it going to be the double bond O one going to attack, or is the OH one going to attack? So I'm showing those two cases, and The left one where I protonate the OH does not happen, whereas the other one does happen. And why is that? This is because, why does this oxygen get protonated? Well, we saw this extensively in chapter 17, which was the nucleophilic addition to ketones and aldehydes chapter. But this oxygen, when it gets protonated, this is an RSCC, right? So there's actually an additional resonance structure too of the carbocation. So there's these two and also a third resonance structure, and yeah. So that is why when we have a carboxylic acid and we're going to protonate it, we're going to protonate it from the acetyl window. Okay. Okay, and I also mentioned that salts of carboxylic acids are useful pharmaceutical preparations, and an example is naproxen sodium or Aleve, where they take the carboxylic acid, which is an actual pharmaceutical, but they react it with sodium hydroxide, takes the proton, leaves you with a sodium salt, and it's a carboxylate, right? It's a carboxylate of the carboxylic acid, and this is the actual pharmaceutical that people use because of the it's easier to handle. I think it might also dissolve a little better in your stomach because it's already ionic. This is O minus Na plus. I think it might dissolve in your stomach acids a little better. Okay. Okay, that's the PowerPoint. Now we're going to switch back to whiteboard. No whiteboard. We're going to switch back to the piece of paper. All right, so now we're continuing onward into carboxylic acids and the reactivity of them. So this is chapter 19, carboxylic acids. And we talked about the properties of them. That was like 1 through 4, which was the PowerPoint, right? And now we're getting into the chemistry. So the chemistry of carboxylic acids. We'll start with the preparation of carboxylic acid. Preparation of carboxylic acids. Okay, so first way to prepare them is from oxidation. So bracket O bracket is oxidation of a primary alcohol. Oxidation of a primary alcohol. So recall that if you have a primary alcohol, there are a couple steps in oxidation state you can imagine. Primary alcohol, aldehyde, and carboxylic acid. Okay? And that if we go from the primary alcohol, we can do this with PCC. Let's draw this larger. Oxidation of primary alcohol. Okay, and that the reagent is PCC, and we often add DCM in the mixture, DCM dichloromethane, PCC. Okay, and if we want to keep going from the aldehyde to the carboxylic acid, there was a way to do that. We learned this, I think, maybe mentioned in Organic 1, but we use CrO3 in acid. CrO3 in the acid will turn the aldehyde into a carboxylic acid. So we go from an primary alcohol to an aldehyde with PCC, or then you can go from an aldehyde to a carboxylic acid using CrO3 and H3O. How would we do this? How do we go all the way in one step? How do we go all the way from a primary alcohol all the way to the carboxylic acid? Well, we can do that with CrO3 acid also. CrO3 and acid. Okay? So we have a couple ways to do this. We could either do a two-step oxidation, primary alcohol to an aldehyde, PCC, and then aldehyde to the carboxylic acid with CrO3 and acid, H3O. Or we can do it all in one step, primary alcohol all the way to the carboxylic acid. Okay. There's also another way to go from the aldehyde to the carboxylic acid selectively, which is Hg2O, silver oxide, Hg2O, and NH4OH. This is selective, so this only oxidizes aldehydes to carboxylic acids. We're just introducing this. This is not like a commonly used oxidizing agent, because it uses silver, and of course silver is really expensive. But anyway, it is a way to go from an aldehyde to a carboxylic acid. Okay. All right. So another thing is if we're let's talk about the mechanism from the carboxylic acid. From the primary alcohol all the way up to the carboxylic acid. Let's think about the mechanism for that. Okay. Okay, so let's show the mechanism from primary alcohol all the way up to the carboxylic acid. I'll do that on a new sheet. Oh, actually, before I do that, the really important thing is the acid, the H3O plus. That is absolutely crucial. Star. So the acid is going to play a central role in how this oxidation works. Okay, so we can go from the primary alcohol all the way up to the acid, CrO3 and H3O plus. Okay, so let's show that mechanism. Primary alcohol we're going to show the mechanism first to the aldehyde, and then up to the carboxylic acid. Using CrO3 and H3O. Okay, so how does that work? Well, you should have learned the mechanism for alcohol plus chromium to the aldehyde, and let's review that. That should have been talked about in Organic 1. So there's CrO3, right? Cr, triple bond, double bond O, double bond O, double bond O. And all we do is have oxygen attack chromium. And now the oxygen is attached to the chromium, okay? Okay, and we have any charges? We have the O minus, any other charges? Got a positive charge right there. Okay, so all we're focusing on trying to get to the aldehyde right now, okay? Okay, the first thing that happens now is we just lose that proton, minus H plus. Lose the proton on oxygen. So the proton's gone. Now what we're going to do is take off the other proton, off the carbon, okay? Take off the proton off the carbon. So water takes this proton off, kicks electrons to make a double bond O, and kicks this guy off as chromium. So actually, one more arrow, and that's like onto one of the oxygens, okay? All right, so that's how we get to the aldehyde. I probably have mentioned this. I definitely mentioned this in Organic 1, but why is chromium a good oxidizing agent? Why is chromium a good oxidizing agent? What is the oxidation state of chromium? It's got double bond O, double bond O, double bond O, right? How many bonds to O are there? 6, right? So it's chromium 6. Chromium 6, right? Chromium 6. And after oxygen attacks, what's chromium now? It's still chromium 6. 1, 2, 3, 4, 5, 6, okay? Still 6. 6. And after we kick it off, though, now it's chromium 4. Four. Okay. 4. And that's kind of why it happens. Why chromium 6 is a good oxidizing agent. It's because it's kind of an unstable oxidizing agent. It doesn't like to be 6. It'd rather be a lower number, like 4. So oxygen attacks, lose proton, lose the CH, and then it goes from 6 to 4. And that's kind of the thermodynamic driving force for how chromium acts as a oxidizing agent. So now what do we do? You think we need to attack chromium again, right? You'd think we need to attack chromium again, right? Like nucleophilically have the aldehyde attack chromium. You'd think we need to do that, right? Problem. Aldehyde's not a nucleophile. It's actually an electrophile. It wants to be attacked, right? Things attack aldehydes. Generally speaking, aldehydes don't go attack other things. Okay? So what we need to do now is use water, which is in solution. Use water, and there's also acid, H+, right? So we have aldehyde, we have water, we have acid. Think back to the beginning of chapter 17, which was back in the old whiteboard days of this course. And what was the first reaction we learned in chapter 17? Aldehydes react with water and acid. And the water attacks the aldehyde and makes a this thing. What's that called? It had a name. It's a hydrate. Hydrate. Hydrate is another functional group, right? It's basically a dialcohol. It's a dialcohol. The aldehyde reacted with water and acid to make this. Incredibly easy mechanism. I'm not going to do it. Oxygen, top oxygen grabs proton, and then water attacks. And then you lose a proton. Review it, hydrate formation. It's a very easy mechanism. Okay, now you have an alcohol. Now you have a dialcohol. Now you do the same exact thing again. CrO3 and lose 2 protons. Just like we just showed. Pick an oxygen, attack chromium, and then just like we did before, we lose proton off oxygen, lose proton on carbon, and we're done. And now we have done the full oxidation from a primary alcohol to an aldehyde to a carboxylic acid. Okay. Another side note: if you have a secondary alcohol or something and you want to go to a ketone, what's the oxidation reagent for that? You should know it. It's 3 letters. It's PCC, right? PCC. Structure of PCC is chromium, PCC is this whole thing, right? PCC, pyridinium, it's an N+, chlorochromate, PCC, is this. Chromium 6, it's a chromium 6 with a pyridinium plus charge on there. Okay, so actually let's change this from a primary alcohol to an aldehyde. Okay, primary alcohol to an aldehyde, all right? So, primary alcohol to an aldehyde, what is the solvent? That's a question you may have not considered, but it's actually dichloromethane, DCM, which is H2CCl, Cl2. CH2Cl2. CH2Cl2. Dichloromethane is a solvent. Okay? And why does this stop at the aldehyde and not go on to the carboxylic acid? We probably never thought about that before. We always teach you that if you want to do a single step oxidation, we use PCC, right? Primary alcohol, PCC, aldehyde. Why does it not continue on to the carboxylic acid? Why does it stop here? And what dichloromethane? Is that water? Is that acid? There's no acid or water, no H2O. It's anhydrous. Okay? It's anhydrous. This is an anhydrous reaction. Primary alcohol, PCC, aldehyde. Because if you did have water and acid, or even just water, what would water do to the aldehyde? It would convert it to the hydrate, right? Just like we saw up here. It would make the hydrate, and then the hydrate would oxidize to the carboxylic acid. So now we know why PCC stops at a single step oxidation. It's because you don't have water. It's an anhydrous. You use an organic solvent like dichloromethane. Okay. And what's the structure? Yeah, PCC. If you wanted to do the mechanism or review it, it's the same thing. Oxygen attacks chromium, kicks onto the oxygen, and then you lose 2 protons. So your oxygen attacks, and then you lose the OH proton, and then you lose that H. So that's the mechanism. It's the same thing as we just did up top. But the big difference is that PCC does not have water, so it's a single step oxidation. Okay? Cool. That's how PCC stops. One more question. One more question. Let's just take this one step further, okay? I'm going to give you just a little paper here. What about why don't we just use CrO3 and DCM? Wouldn't that do the same thing? CrO3, primary alcohol, CrO3 to aldehyde. Would that do the same exact thing as PCC? PCC, right? I mean, why do we even have PCC? Why can't, just like we take primary alcohol and react it with PCC and DCM to make an aldehyde, why can't we just take a primary alcohol and do CrO3 and DCM, right? Because that would do the same thing. This is an organic solvent, no water, stops at the aldehyde. This is also an organic solvent, stops at the aldehyde. Why do we even use PCC? Why don't we just use bottom one, CrO3 DCM? The problem is it's insoluble. Insoluble, doesn't dissolve. That will prevent a reaction from happening. CrO3 does not dissolve in dichloromethane, so this reaction won't go. Big X. Okay? PCC was kind of created, it was invented. I mean, it was because it's able to dissolve in dichloromethane. And you know, that somebody actually figured out and designed PCC. It's a human-created reagent that is dissolvable in an organic solvent like dichloromethane and easily allows the oxidation from primary alcohol to an aldehyde. Okay, so that was an interesting little side point too. Okay. All right, so we were just talking about preparation of carboxylic acids, or CO2H, preparation of carboxylic acids. And that was oxidation of alcohols. What's another way to make carboxylic acids? Another way to make them is reacting in a Grignard, R, MgBr, a good nucleophile, or you could do R lithium. So both of those are good nucleophilic carbon reagents, right? Grignard, and what's the name of this? Organolithium. Organolithium. And with CO2, so we're going to react a Grignard or organolithium with CO2. Okay, very easy method. So let's just show an example. First, how do you make a Grignard? We'll take maybe a bromobenzene, throw in some magnesium. Again, this is also a case where water is really bad, so you use usually THF or like dry THF. But we often omit solvents in when we're learning this stuff. But yeah, it's dry THF usually. Grignard, okay, so if we want to make it carboxylic acid, just react it with CO2. And then H3O plus. And what do we get? Carboxylic acid. How does it work? Very simply, the Grignard attacks the electrophilic carbon. Why does it attack it? Because it's delta negative, right? Delta positive, right? So the middle carbon is delta positive, and the two oxygens are delta negative. Electrons go, up or down. And how do we finish off the mechanism? H3O plus. Yeah, that's pretty easy. That's a way to convert a Grignard to a carboxylic acid. What's the name we gave to these things? It's kind of like halfway to a carboxylic acid. It's a carboxylate. Okay. Anything else? What's the counterion right now? O minus something plus, right? It would be MgBr plus. Okay. We often omit the counterions. Yeah. Okay. Cool. So there we go. That's one way to make a carboxylic acid. A was to oxidize an alcohol. B is to react a Grignard with CO2. Let's show an example of it. How can we convert this bromide to this carboxylic acid? And this is actually a drug. This is called Fenno Profane. Fenno Profane. F-E-N-O, Profane. P-R-O-F-E-N. It's an NSAID, non-steroidal, anti-inflammatory drug, kind of like ibuprofen or something. Well, there's a three-step process. 1, 2, 3. Synthetically, how do we do this? We need to we're trying out this Grignard method. So maybe first you make a Grignard, then you throw in something, and then you throw in H3O, right? Magnesium, CO2, H3O. Okay, so now we know a way to convert a alkyl bromide to an alkyl carboxylic acid. Okay, Fenno Profane. Okay, and this is kind of complementary to another thing you learned. So we should just mention it. Is what if we do magnesium and then H3O is the last step? Because what other one-carbon electrophiles do you know? Like things that we can react that are the Grignard. A Grignard will attack. It's a one-carbon electrophile. Like formaldehyde, right? So this is kind of the same idea. Formaldehyde. Make a Grignard, attack formaldehyde, and then H3O plus. What's the product of that? What do you make? What do I draw there? That when we make a Grignard and attack formaldehyde and H3O, what is this functional group now? Because if you have a Grignard attacks this, kicks electrons up, it's actually going to be a primary alcohol, right? So yeah, and of course we could convert this primary alcohol to the carboxylic acid. How? CrO3 acid, right? That would actually oxidize the primary alcohol to the carboxylic acid. Okay? So how could we make or synthesize naproxen by this method? Naproxen, which is Aleve, the painkiller. How would we do that? So this is naproxen. I could envision kind of, draw a squiggly line, and that's where we maybe make a connection, and then you could synthesize this from the bromide. So right, 3 steps. Make a Grignard, throw in CO2, carbon dioxide, and then throw in acid. So it's a 3-step. You can fill in those 3 steps, okay? How do we deal with CO2 in the laboratory? I'll write CO2 for step 2. How do we deal with CO2? I mean, do we just go get a tank of CO2? It's magnesium. Make a Grignard, CO2, and then acid. How do we actually deal with CO2? Do we just get a tank of CO2? Well, that's possible. CO2 is a very cheap gas, so you can just go buy a tank of it. But you could also just use dry ice, because dry ice is CO2, right? Dry ice is CO2. Okay. Okay, cool. And one more thing about this reaction. So when we often make bonds, and certainly carbon bonds, CC bonds, we often have to worry about like sterics, like is a nucleophile too hindered or something like that. And you might imagine that, like, if we turn this guy into a Grignard, that it might be too hindered to attack, right? Attack stuff. Well, Grignards are not usually problematic like that. So Grignards are sort of forgiving with their like steric hindrance and stuff. So this reacting with CO2 and then H3O will totally react. And the other thing is that H3O, in addition to being the second step of the Grignard, would probably deprotect this this guy. This is a protected something, right? It's a protected ketone. Protected ketone. This will come off with H3O. So here we can actually do two steps in one. So we can attack CO2, and then we can be protonated by H3O plus, and it'll also cause deprotection of a ketone. So this will give us this is our final product. Okay, that's very nice. All right, so next we have we're still doing the preparation of carboxylic acids. We did oxidation, we did the Grignard with CO2. Third one is from hydrolysis of carboxylic acids. Nitriles. My bad. Nitriles. From the hydrolysis of nitriles. Okay, so let's show an example of this. What's a nitrile? A nitrile is like C triple bond N. Okay? Nitrile. Okay, so we can hydrolyze a nitrile, which is 3 bonds to nitrogen, and we can convert it to 3 bonds to oxygen, which would be C double bond O, OH, right? So 3 bonds to nitrogen to 3 bonds to oxygen. Let's see an example. And let's also quickly review, how do you make a nitrile? How do you make a nitrile? Like, an easy way to do it is Sn2, right? So it's C triple bond N. And you just use like Na plus Cn minus, right? Circle, attack. That's really easy. It's an Sn2 reaction. That's how you make a nitrile. Okay? Alright, what else? So what's a good Sn2 solvent? So if you want to do an Sn2 reaction, you need a solvent. Usually DMF is one of the good ones. We learned that in Organic 1. Okay? Alright, so then once you got a nitrile, we can hydrolyze it. Hydrolysis of nitriles. So how do we do that? Very easy methods using H3O plus. This is a little bit of a mechanism, so give yourself some space when you copy this down. What's the mechanism of how this works? How we go from a nitrile to a carboxylic acid. It's a fun mechanism. It's a great exam or quiz mechanism. But anyway, H3O plus is also, it's H plus and H2O, right? So it's got H plus in there. So what we're going to do this mechanism is start by protonating the nitrile. Start by protonating the nitrile. C triple bond N H plus. Using what we did before, you could call this an RSCC, right? And it's electrophilic, and you could push electrons onto the nitrogen. I guess maybe I'll do that. Yeah, I'll do that. You don't have to do this, but I think it helps when you're learning this stuff to draw out these RSCCs. Maybe I'll do this one, but the other ones in this mechanism I won't do. Okay, so now we have water attack. Water is going to attack that RSCC. It's a nucleophile. Okay, so what do we get? Water is going to be attached now. Okay, and what do we always do after nucleophilic attack? We proton transfer. From where to where? From oxygen to nitrogen. Oxygen to nitrogen. Now we have another RSCC. To save space, I'm not going to draw out the RSCC. I'm just going to write the letters RSCC, and I'm going to have water attack it. So our water attacks. Where do the electrons go? Onto the nitrogen. Water attacks, electrons go onto nitrogen. Okay, now we have a new positively charged oxygen. We also have the NH2 and we have the other OH. What do we do after nucleophilic attack? We proton transfer. Usually after nucleophilic attack, we always proton transfer. What's our, oh yeah, the end product is also ammonia. Ammonia will be a byproduct of this reaction. Okay, so what are we trying to make come off as a leaving group? Maybe the nitrogen, and maybe that'll be where the ammonia comes from. So we PT from oxygen to nitrogen. PT now it's OH, OH, and NH3 plus. NH3 plus, right? OH, OH, NH3 plus. Now use one of these oxygens to kick it off. Kick off the nitrogen. Oxygen, lone pair, kicks in, kicks off nitrogen. Almost done, almost done. I'm going to sneak in the intermediate. Oxygen kicks off nitrogen. Now you have a protonated carboxylic acid, and that loses a proton. Minus H plus, okay? So there it is, there's the mechanism. We can step through it real quickly one more time. Start with nitrile. Start with nitrile, protonate it, make an RSCC. Water attacks the RSCC, carbocation. Now you have oxygen attached. After nucleophilic attack, we proton transfer from oxygen to nitrogen. Makes a new RSCC. Water attacks that. And now we have OH, OH2 plus, and H2. Proton transfer. Always after nucleophilic attack, we proton transfer. From this time from oxygen to nitrogen. Now we have OH, OH, NH3 plus. We went from NH2 neutral to NH3 plus. Use one of the oxygens, kick off. Now we have the protonated carboxylic acid, which is the final product, plus a proton. Lose a proton, and you're done. So that is the full mechanism of nitrile hydrolysis. Okay? So this is, as you can imagine, it's complementary to the Grignard method. Not always, because you can't always make nitriles by Sn2, but we sometimes can. Let's let's show that thing we made earlier, Fenno Profane. And show how we could do this using the nitrile method. So how could we convert this alkyl bromide to the alkyl carboxylic acid, but not using Grignard? We'll use the nitrile method. Well, we could just do NaCN, DMF, that Sn2s, carbon attacks, mix a nitrile, and just H3O plus, maybe a little bit of heat will help that reaction out also. H3O plus and heat, okay? And this makes Fenno Profane. NSAID, which is again a kind of a painkiller type drug. Okay, great. The book, I think, may mention also that you can do this by basic hydrolysis. I'm going to skip that, and for this class, I'm not going to focus on this one. This is, you know, it's another way to do this sort of hydrolysis, and what happens is the hydroxide attacks, and there's a series of steps that converts the triple bond N to three bonds to nitrogen, 3 bonds to oxygen, using NaOH. I really like the mechanism of the acid one. It's a cool, very elegant mechanism. So if you're going to learn anything in this course, just focus on the acid-catalyzed hydrolysis of nitriles. All right. Also, hydrolysis of cyanohydrins. Hydrolysis of cyanohydrins is a C. Cyanohydrins. You learned about this one last chapter a little bit. 2 chapters ago. Maybe 2 chapters ago, yeah. Let's just show an example. If I react this aldehyde with HCN, you make this kind of alcohol-looking thing, almost looks like a Grignard product or something, called a cyanohydrin. And what's the mechanism? It's incredibly easy. This protonates that's an RSCC. Cn minus attacks. Nitrile attacks the RSCC. And you get the cyanohydrin. So that's a very easy functional group we can create. I'm skipping the resonance form of this, but that's fine. You could draw it if you like. But anyway, then it's like, well, we got this. Can I do something with it? And maybe convert it to a alpha hydroxy carboxylic acid. So I can convert the nitrile of this cyanohydrin to a carboxylic acid. And how do I do it? Well, you just learned how. H3O. So this is just a different kind of nitrile. It's similar to the other nitriles, but H3O plus will do that crazy long mechanism, arrow, 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 that we just did, that full mechanism. Protonate the nitrogen, water attacks, proton transfer, blah, blah, blah. So review that. But yeah, this is another thing we can do, is that we convert a cyanohydrin to a alpha hydroxy carboxylic acid. Why is it alpha hydroxy? Because the hydroxy is in the alpha position, next door to the OH. Cool. Okay. One more thing, and this one will be maybe this chapter or next chapter. There's one more thing you can do to nitriles. That's kind of a new thing, but you can reduce them. Lithium aluminum hydride. You can reduce nitriles with lithium aluminum hydride and H3O. And it goes from 3 bonds to nitrogen to 1 bond to nitrogen. So it's a double reduction. And that makes so yeah, you can convert cyanohydrins to these sort of amino alcohols. Okay? This is soon, we'll say. Soon. But it's not. It's actually very easy. It's just H minus attacks, and then it attacks twice. H minus attacks once, H minus attacks twice, pushes onto the nitrogen, and then a little bit of water, and then you get the amine. So it'll be a very easy mechanism. We will see that one soon. Okay, in the last couple seconds, I think we're done with this lecture. I'm just going to mention what the next section is so we can think about it. It's going to be called Carboxylic Acid Derivatives. And so this will be a big section, and I'll just mention what they are and then we'll stop. So it's kind of like a carboxylic acid derivative is sort of anything that looks kind of like this. So it's like a C double bond O and a leaving group. I'm going to just list them and then stop. Okay, so let's just make a list. So next time you'll know what I'm talking about. And give them names. Okay, so these are the main carboxylic acid derivatives that we're going to talk about in this class. Let's just give them all names. Okay, this is an acid chloride. Acid chloride. We've seen acid chlorides a couple times. Friedel-Crafts reaction, maybe a little bit of protection stuff. This one you may or may not know. It's called an anhydride. Anhydride. So an anhydride is kind of like this C double bond O, oxygen, C double bond O. That's called an anhydride. This one you should know from Organic 1. It's called an ester. This one you should also know. Acetyl nitrogen, and it's an amide. And then this one, of course, is a carboxylic acid. Okay, so what we'll do is next time we'll talk about the reactivity of these things, how to make each of them, etc. Okay, all right, thanks. Yeah, I'll have a lecture in a couple days. See you guys.